Chapter 4 takes a look at what are called discrete random variables, which are some specific types of random variable models. So the question we're going to take a look at, the essential question we're going to follow, are what are some probability models. In other words, models that can be used to represent various probability situations. And we're going to set this up with what are called probability distribution functions. And we're going to abbreviate probability distribution function as PDF. And probability distribution functions describe what are called random variables, which are outcomes of experiments. When we represent the random variable, we will use a capital letter to represent the random variable in words and a lowercase variable to represent it in numbers. So a lowercase x is a number, a capital X is some word description. So let's do an example of what a probability distribution function would be. An example, we might be interested in the number of times a baby will wake its mother during the night. We'll use lowercase x to represent the numbers. So the baby could wake the mom up 0 times, 1 time, 2 times, 3 times, 4 times, 5. We're going to stop at 5, no more than 5 times. And then what the probability distribution function will do, the PDF, is it will assign a probability to each of these values. Maybe the probability of 0 times is 0.04. The probability of 1 time is 0.22. Twice is 0.46. 3 times is 0.18, 4 times is 0.08, 5 times is 0.02, and maybe some of you with young kids are saying it's much more than that. But we're going to go for that for now. One thing that's important about the probability distribution function is that if you add up all the possibilities, it does add up to 1. The probability that the kid's going to wake him up between 0 and 5 times is 1. It's going to happen. One of those values. And with probability distribution functions, what we're often interested in is finding the expected value of the distribution function. What we expect to happen. In other words, the long-term average. Kind of like saying the mean that we saw before in descriptive statistics. And the way we find the long-term average is we will take the sum of all of the x's times the probability. So we're going to take x times the probability of x. So 0 times 0.4 is 0. 1 times 0.22 is 0.22. 2 times 0.46 is 0.92. 3 times 0.18 is 0.54. 4 times 0.08 is 0.32. And 5 times 0.02 is 0.10. If we add all of those up, we get, grabbing a calculator, 0.22 plus 0.92 plus 0.54 plus 0.32 plus 0.10, 2.1. So the average expected value is 2.1, which means on average a mother is going to wake up 2.1 times per night with her baby. That's the expected value. Another thing we might be interested in, as you might expect, is the standard deviation. Probably should have stuck a Greek letter in here because this represented all the possibilities of waking up. So we're going to say mu, the expected value. The standard deviation, sigma, Greek letter because it's everybody, all the possible times a person could wake up, not just in our survey. The standard deviation is the square root of the sum of the probability times the difference between x and x bar squared. Notice this looks a lot like the standard deviation formula for a frequency. The probability is the relative frequency of that event, so it makes sense that they're related to each other. So first we need to figure out, working our formula inside out, what x minus x bar is. So x minus x bar. We're subtracting 2.1. 2.1 is our x bar, or it should be mu, actually, would be even better. Let's go ahead and change that. Let's make that mu in our formula. The average. So again, doing the parentheses, x minus mu. Mu, we've already found out, is 2.1. So 0 minus 2.1 is negative 2.1. 1 minus 2.1 is negative 1.1. 2 minus 2.1 is negative 0.1. 3 minus 2.1 is 0.9. 4 minus 2.1 is 1.9. 5 minus 2.1 is 2.9. Next part of the formula asks us to square that value. So x minus mu squared. So 2.1 squared is 4.41. Notice when we square, everything's positive. 1.1 squared is 1.21. 0.1 squared is 0.01. 0.9 is 0.81. 1.9 squared is 3.61. And 2.9 squared is 8.41. Formula says the probability times that. So we're going to take the probability times x minus x bar, or actually it should be mu, x minus mu squared. Basically we're multiplying the probability column by the x minus mu column. 0.04 times 4.41 is 0.1764. 1.21 times 0.22 is 0.2662. 0.01 times 0.46 is 0.0046. 0.81 times 0.18 is 0.1458. 3.61 times 0.08 is 0.2888, and 8.41 times 0.02 is 0.1682. The formula asks us to find the sum, which means we're going to add all of these together. 1764 plus 2662 plus 46.0046 plus 0.1458 plus 0.2888 plus 0.1682 is 1.0498. The standard deviation is the square root of that. The square root of 1.0498 which, when we type that into our calculator, we get 1.025 approximately for our standard deviation. Now that's all nice and dandy if we have a table for our probability distribution function. However, what we're going to be more interested in for our work, both today and moving forward, are what we're going to call the common probability density or distribution functions. Densities. Next chapter, sorry. There's going to be 3 common PDFs that we're going to look at today. We'll look at a new one tomorrow, and then eventually we'll get into the big one, which is the normal distribution. So we've got several of these we're going to see. Today we're going to start with what is called the binomial probability distribution function, which tells us the probability of X successes in N trials. The notation your book will use for a binomial is we'll say X is the random variable. It is a binomial, and then we're going to put 2 arguments in the binomial. We'll say the number of things we're working with, and P, the probability of a success. Couple key points to describe the binomial. First, with binomials, there are only 2 options. Success, which has a probability of P, and failure, which we say has a probability of Q. And what's important here with that is P plus Q. The probability of success plus probability of failure has to be 1, because you either succeed or you fail. What's nice about this common PDF, though, is we don't have to go through all the work to calculate mu, the average, because if we know the number and the probability of a success, we just multiply the number times the probability of success, and that tells us the binomial distribution's average. The standard deviation is the square root of NPQ. Q is the probability of failure. And what's nice is we can do this on the calculator to calculate probabilities. If we want the probability that X is equal to some lowercase x value, on the calculator, we will use the second button and then the distribution function button. And I'll show you where that is here in just a minute. I'll pull up my calculator. But what we're going to select is binom PDF, and then we're going to type in the number of trials, the probability of success, and the number of successes we want to hit. Now, a slight variation to that is sometimes we want to know when X is less than or equal to some value. When we want less than or equal to, this is asking for the cumulative relative frequency, or the cumulative probability all the way up to X. The main difference is we're going to select a different option. It's the CDF of NPX, the cumulative distribution function. And again, I'll show you how that works specifically on the calculator when we work out an example here. So let's do that. Let's say 41% of adults have a high school diploma. In a certain community. If 20 are selected randomly, we're going to be asked to find first we're going to find mu. Mu, you remember from option B, is the number times the probability of success. So the number is 20. The probability of success is 0.41. So on average, 20 times 0.41 is 8.2. So if we ask 20 random people, on average, 8.2 of them will have a high school diploma. course, we might be interested in the standard deviation, which we have from part C. The formula is the square root of NPQ, or the square root of 20. Probability of success, the probability they have that diploma is 0.41, times Q, which is the probability of failure. Well, if success is 41%, failure must be the opposite of that. 100 minus 41 is 59.59% then is the probability of failure. So we'll do the square root of 20 times 0.41 times 0.59 and hit enter. We have a standard deviation of 2.2 roughly when we round. So now we know in this situation an average of 8.2 with a standard deviation of 2.2 will have a high school diploma. So let's find the probability that x equals 8, or the probability that we have exactly 8 who have their high school diploma if we ask 20. That's what we expect to happen, so let's find out if that's what happens. Okay, on the TI-84 calculator and the TI-83 calculator, the location of the feature is the same. The 84 is nicer in that it gives you a few prompts to get you what you want, but I'll talk about both options. If we hit the second button in the top left, and then right underneath the down arrow, above vars, you see the word distribution. Under distribution, there's a lot of options. We're going to be interested in the binomial probability distribution function. And it's quicker to get there by scrolling up, because that takes you to the end, and then if you keep going up, you will see binomial PDF, opening a parentheses. Select that one, and if you have the 83, it's going to open up a parentheses ready for you to type in the same data values that we're going to type in on the 84. The 84 is nice because it gives you prompts. It says, how many trials are there? Well, we had 20 randomly selected adults with a probability of 0.41, enter, and we want to know if our x value is equal to 8, enter. And when we select paste, it's going to stick it in there. The 83 calculators would have had to type 20, 0.41, 8. Either way, when we hit enter, you'll end up with our probability, which is 0.1790. So the probability that you actually get 8 is 0.1790. What if we want the probability that we get less than or equal to 5 values? Because we want less than, we want everything up to 5, this is going to be a cumulative distribution, because we want 0 plus 1 plus 2 plus 3, cumulative, adding them all up. Same place, second distribution, but this time instead of the PDF, we want the CDF, because the C stands for cumulative distribution function. Type in the same information. We've got 20 trials because we selected 20 people. Our probability was 0.41, and we want to go all the way up to 5 people. Paste it in there. If you had the 83, you typed in 20, 0.41, 5. Same result. Hit enter, and we get 0.1079. 0.1079. We can start to get a little more creative. Let's say we want the probability that we have more than or equal to 9. Now, we don't have a CDF that will do greater than or equal to 9. So what we need to do is we're going to take 100%, all the possibilities, and we will subtract off the cumulative distribution as x goes up to and equal to, be careful here, on the left side, do we include 9? Yes, we do. So on the right side, we do not want to include 9, so we're only going to go up to and equal to 8. Notice this would be different if the probability was just greater than 9. Then we would do 1 minus the probability of x going all the way up to 9. Because 9 was not included on the left, when we subtract it off, we would want to include it on the right. So on the calculator, what we're going to type in this time is 1 minus, and then the same process. Go to the distribution, going up because it's quicker, to get the CDF because it's a cumulative distribution function. 20.41. This time we're going to go up to the number 8 and hit paste. And when we hit enter, we get a probability of 0.4406. 0.4406. So the probability that 9 or more people had a diploma is 44%. And so using this process, we can get creative to grab any grouping of people we're interested in studying for this probability problem. So that's the binomial. What's the probability that x out of n are a success? The second type of probability distribution function that we're going to look at is called the geometric. And the geometric is very similar to the binomial in that we still run n trials, but what we're looking for is how long until we get that first success. Binomial is 3 out of 5 successes or something like that. Geometric is interested in how long until we get the first success. How long are we going to have to work at it till we find one that's successful? Probability of n trials before the first success. And the way we show that the random variable x is a geometric, and the only thing we care about is the probability of a success on any given trial. Mu, in this case, the average, is going to be the reciprocal of that probability. It's the average length it's going to take before you get a success. The standard deviation formula turns out to be the square root of 1 over p times 1 over p minus 1. And on the calculator, it's very similar to what we did before. You're going to again go second distribution. And if we want the probability that x is equal to some numerical lowercase x value, this time we're going to grab the geometric PDF. We'll do the probability first, then we'll do the number of trials that we're going for. If we want to do a less than or equal to situation, again, that's cumulative all the way up to x. It's going to be geometric CDF again, cumulative distribution function, probability, comma, n. So let's try an experiment. An example. Let's say the probability I got an extra B in there. Probability of a defective part is 0.02. 2% of the parts are defective. We're going to find the probability the first defect is on part 7. And actually, I'm going to preface this with first identifying, just for the sake of running through the formulas, the mean and the standard deviation. Not because it's part of the question, but just that we can practice using the formula. The mean is 1 over the probability of 0.02, so the mean is going to be 50. So on average, you can go 50 parts before you have a defective one. It's going to be a really small probability for 7. Let's say 47, part 47, so that we don't get a 0 probability because it's so rare. Standard deviation, sigma, is the square root of 1 over 0.02 times 1 over 0.02 minus 1. And we can just type that directly in our calculator. 1 divided by 0.02, open a parentheses, 1 divided by 0.02 minus 1, and close the parentheses. And we get 49.40.5, really. So it's quite the deviation. So now let's actually answer that question. First defective part is part 47. We're asking for the probability that x is equal to the 47th part. On our calculator, again, we'll hit second, distribution. Up's the quickest way to get there, and actually the last two, you notice, are the geometrics. Because we want to actually equal 47, we're going to go to the PDF. And again, on the 83, you type in these numbers separated by commas, which are right next to the parentheses. Here, we're just going to type in the probability we said was 0.02. The x value we wanted was 47. And we're going to paste, and there's the geometric PDF, just like you would type it on the 83. Hit enter, and we get 0.0079. 0.0079 is the probability it would happen on the 47th attempt. What if we tweaked it and said, what is the probability that you can go 47 and you still haven't hit it? What is the probability that x is less than or equal to 47? That's the probability you find a defective part within the first 47 trials. Again, that's a geometric, but this time it's cumulative. Same probability, 0.02. The x value, 47. Paste it on there. Cumulative distribution function, we've got the CDF. It's equal to 0.6131. 0.6131. There's a 61% chance you will find a defective part amongst the first 47 parts. That is the geometric distribution. How long until the first success? Another distribution I want to take a look at is called the Poisson distribution. Poisson was a French mathematician, often confused with as the poisonous mathematician. Poisson, that was a pun, not a historical reference. Poisson found a probability model that looked at the probability that a certain number of events would occur in an interval of time. So we're going to say the probability of x events in an interval. Often we talk about time. How many accidents are going to occur in the next week? It's the number of events that occur over an interval of time. And the way we represent this random variable x is with a p for Poisson, and then inside Poisson we'll stick the variable mu, or the average. It's also interesting to note this is very similar to the binomial, especially if p, the probability, is small, and n, the number of trials, is large. And those words are in quotes because there's no real hard rule about what is small and what is large. But Poisson and binomial have a lot in common because we might be talking about the events being a success, and then we're kind of talking about a binomial. One example is if you look at a novel and the number of typos in the novel. Well, there might be a binomial because there's only a certain number of pages and we want to know how many pages have a typo. But it might be a Poisson because the same page might have 2 errors in it, and that counts as 2 errors, so it's a Poisson distribution. So it's really tricky sometimes to tell the difference, and the reason is because, well, you get real similar answers anyways. But the big thing that defines a Poisson is you get so many events in an interval, usually of time, an interval. What's nice about Poisson is we know what the mean is. The mean is just mu. The standard deviation is easy. It's actually the square root of mu. And on the calculator, you might guess we're going to hit second, and then we're going to go to distribution. And again, there's a cumulative distribution function and a probability distribution function. If we want the probability that x is equal to some lowercase value x, we're going to use the Poisson probability density function. We will put mu in so we know what the average is, and then we'll type in the number that we're interested in working with. If we want to know the probability that x is less than or equal to some value, that's going to be a cumulative distribution function, again of mu x. So, let's say a reporter says 2 times per broadcast. And you notice a broadcast is a period of time. So we're going to look at how many times he says over the course of time in the broadcast. First, what is mu? Mu is the average number per broadcast. Mu is 2. What is the standard deviation? The standard deviation is the square root of mu, the square root of 2, or about 1.41. So let's see if we can find the probability he says more than 2 times. What we're really saying is, what is the probability that x is greater than 2? Well, cumulative distribution functions would go up till 2. So we need to do 1 minus the probability that x is less than or equal to, and what's the smallest value it can be equal to? 2. Because 2 was not included on the left side. When we subtract it off, we want to make sure it is included on the right side. So we type in 1 minus second distribution. Again, we're going to scroll up, and you see between the binomial and the geometric is the Poisson. We're going to do the cumulative distribution function because we want to go all the way up to a value. Now here's an important difference, is the calculator is going to ask you for a lambda. Lambda is a different Greek letter, but it means the same thing as mu. It's asking for the average, the 2. We want to know the probability that it is more than 2, that he says it more than average, which is also a 2. We paste that in, hit enter, and it's going to say 0.3233. 0.3233. 32% of the time he says it more than average. So today we took a look at probability density or distribution functions. Talked about the 3 main ones, the binomial, the geometric, and the Poisson. Take a look at those on the homework assignment. We're going to go through each of those on the practices and in the lab. So we will see you in class.